A vector space is a non-empty set V of objects called vectors on which are defined two operations, and those are called addition and multiplication by scalars, subject to the 10 axioms listed. These 10, I'm not going to read them out. They are in your Google Drive folder under Unit 3, and you can either have those pulled up on another device or print them off. The 10 axioms must hold for any vector u, v, w, and any scalar c or d, where c or d would be real numbers. Okay, so let's look at an example of a vector space. Let V be the set of all arrows in three-dimensional space with two arrows regarded equal if they have the same length and point in the same direction. Define addition by the Parallelogram Rule, and for each V in vector space V, if it's lowercase, it's a vector. If it's uppercase, then it's usually vector space. Define CV to be the arrow whose length is absolute value of C, which is C is a scalar, times the length of V. So in other words, 2V would be a vector that points in the same direction as V, but it's twice as long. And we've looked at vectors before. C is going to be non-negative. In other words, greater than or equal to 0. If it's 0, you have a 0 vector. Otherwise, pointing in the opposite direction, and that would be if your C value is negative. So if it's negative 3V, it would be 3 times the length of V, but it would go in the opposite direction. Okay, so we're going to show that V is a vector space. An arrow of 0 length is a simple point and represents the 0 vector. So that's one of your axioms. The negative of V is just negative 1 times V, or you can actually write negative 1V. So axioms 1, 4, 5, 6, and 10 are held, and they're evident since V is geometric. Now, as far as the other axioms go, using concepts of length and direction, let's take vectors U and V. U plus V, if you go tail to head, would be a direct shot across the bottom. That's U plus V. This is where you would land from start to finish. If you did V plus U, that takes you to a location where if you started at V and finished at U by the parallelogram rule, U plus V is the same as U plus V is the same as V plus U. Now, if you throw a third vector in here, we have U, V, W. U plus V takes you here, and then when you add W, that takes you here. Now, if we do V plus W, U plus V plus W, guess what? It took us to the exact same location. So whether you add the first two vectors and then the third, or take the first vector and add the sum of the next two, you can tell where geometrically V is a vector space. For n greater than or equal to 0, the set P sub n of polynomials of degree at most n consists of all polynomials of the form P of t, so you'd have a constant as long as it's not 0, the coefficient of the linear term, the coefficient of the quadratic term, all the way to the coefficient of the nth term, where coefficients a0 through a sub n and t all belong to the real number set. The degree of P is the highest power of t whose coefficient is not 0 if P of t is equal to a constant that's not 0, then the degree of P is 0. In other words, a constant, you can write a variable next to it. It'd be like a t to the 0. You're just not required to. So that's a degree of 0, as if you have a non-zero constant for your function value. If all the coefficients are 0, P is called the 0 polynomial. So the 0 polynomial is included in the set P sub n. Given P of t above, and that's just the general form for it, and let's add in another function, Q of t, and I'm just going to make the coefficients B sub instead of A sub. If we were to add these together, and we're checking for closed in addition, is what we're doing, and that's from one of the first 10 axioms. Closed in addition means that you take two vectors or two polynomials. If they belong to the original set, then their sum should also belong to the same set. So if we add P and Q, which spread out's P of t plus Q of t, we would add the constants together, the linear coefficients together, all the way up to the final power, and those coefficients would be added together. You can tell by the format that you have a constant, a linear. Here would be a sub 2 plus b sub 2 times t squared. That would be your quadratic set, all the way up to n. Scalar multiplications, if you take some real number and multiply it times your polynomial. So c times p of t would be the same as multiplying each term of the polynomial by that number. So, like say for instance you had f of x equals 2x plus 3, and you were doing 2 times that, then you'd have 4x plus 6. You would just double each term. Okay, so the steps here marked with an asterisk, those satisfy axioms 1 and 6. Axioms 2, 3, and 7 through 10 are satisfied from properties of real numbers. The 0 polynomial satisfies axiom 4, and if you negate your function or polynomial, it's the negative of P, satisfying axiom 5. Therefore, P sub n is a vector space. All 10 axioms are satisfied. A subspace of Rn is any set H in Rn that has 3 properties. Now, these properties are also listed back in the vector spaces, but subspace, really you just check for a 0 vector, closed under addition, and closed under scalar multiplication. Subspace is closed under addition and scalar multiplication. So let's look at an example. If V1 and V2 are in Rn, and H is the span of those two vectors, then H is a subspace of Rn. Alright, so first, and this will be example A, I'll have it diagrammed on the next page. Okay, so let's first note the 0 vector is an H, because if you multiply those two vectors by some scalar, specifically 0, you have a linear combination of V1 and V2. Now, let's pick two arbitrary vectors in H. Some scalar times vector 1, some scalar times vector 2. Now, this is just an arbitrary vector using V1 and V2, so we're checking the span. Let's let V be just some other scalar V1 plus some other scalar V2. If you add these, the V1 terms, you add the scalars times vector 1. And then you add S2 and T2 times vector 2. So you got a linear combination of U and V, and therefore it's in H. It's in the span of those two vectors, specifically with these two weights. Number 3, for any scalar C, just think of it as some random number, the vector C times U is also in H. If you multiply C times U, then you have C times this arbitrary vector up here, S1V1 plus S2V2. You can separate that out and think of it as distributing, because S1 and S2 are both real numbers, so is C. So you can multiply those and let these be the weights of V1 and V2. And so you get the span. And that's what we were asked to show, is if we take any vectors, no matter how many entries, N just represents general entries, then whatever the span of those, whether it's on a line through the origin or a plane through the origin, then that span is a subspace of Rn, because all three of these properties are met. Example B, if V1 is not 0 and if V2 is a multiple of V1, then V1 and V2, and that's what I mentioned on the previous slide, was it's simply a span of a line through the origin, because like take V1, if V2 happens to be 2V1, it's just twice as long, or maybe it's negative 3V1, it would run the opposite direction, triple the length. Back on part A, because we had a span of V1 and V2, that actually is a plane where V1 and V2, if you look at the span of it, V1 plus any linear combination of V1 and V2, you're going to fall somewhere on a plane in a R3 environment. Part C, a line not through the origin is not a subspace because it does not contain the origin as required. And that's the very first property. For example, let's take a line that does not go through the origin. Part B does. So as long as one vector is a multiple of the other, you're good to go. If your line doesn't go through the origin, the problem is you can take a vector, namely u, that is on that line, but if you double it, it's no longer on this line. 2u falls out here, not on the line. If you were to add u and v, notice u and v both fall or lay on this line, but if you add those up, u plus v, you land somewhere besides that line. So that's what it means for like closed. Scalar multiplication is not closed, and neither is addition. You can take two vectors that are on a line, not through the origin, but whenever you double, you're not always going to be back on that line, or if you add two vectors, you're not going to always fall on that line. Let P be the set of all polynomials with real coefficients with operations in P defined as you would for functions. Then P is a subspace of the space of all real valued functions defined on R, the real number system. Also, for each n greater than or equal to 0, P sub n is a subspace of P because P sub n is a subset of P. And it contains the 0 polynomial. The sum of two polynomials is also in that same, because you'd add like terms. And scalar multiplication, if you multiply any component or all of a function by a scalar, then that function will also be in Pn. Adding and multiplying by a scalar does not affect the degree, whatever that may be, of your polynomial. The second example on the slide, the set H, let's let it be a 3-entry vector, st and 0, where s and t belong to the real number system. That's a subset of R3 that acts and looks like R2, because think of it if you had like an X, Y, and Z coordinate system. Z and then X and Y. Think of it as being like a one plane through the origin. You don't cover all the R3s because that one's locked in at 0. So this is a case where we're going to show that H is a subspace of R3. The 0 vector will work if S and T happen to both be 0, which are real numbers, then you've got the 0 vector. So that's an H. The 0 vector belongs to H, 0, 0, 0. And that would be the origin and a R3 case. Closed under addition, if I pick any two values for S and T, as long as they're real numbers, and I add them together, the result's going to be some real number, another real number, could be the same, could be different, and 0. That one's always going to be 0. So if you pick any two vectors, U and V, that belong to H, or fit H's description, then their sum will have a real numbers for the first two entries, and that's where the S and T come into play, and a 0 for the third entry. As far as checking for closed under multiplication by a scalar, pick any vector in here. As long as S and T are real numbers, you can pick it up. So it could be 3, 1, 0. Make up your first two numbers and 0. If you multiply them all by a constant, 3 times S, I'm just picking 3 at random. 3 times S will also be a real number. 3 times T, that's also going to be a real number because S and T are real numbers to begin with. And 3 times 0, that's 0. So as far as closed under multiplication, pick a vector that fits this description, pick any scalar that's a real number, and then your vector CU will have real numbers in the first two entries and 0 for the third. Given V1 and V2 in vector space V, let H be the span of those two vectors. Show that H is a subspace of V. So again, for subspace, you don't have the 10 axioms that you do for vector space. We just have to check for a 0 vector. If we multiply V1 and V2 both by 0, we've got the 0 vector. So that's an H. Closed under addition, let's pick two vectors U and W. I don't want to use V because V's already scattered throughout. If we add U and W, S1V1 plus T1V1 is the same as S1 plus T1V1. Basically, it's like you're adding like terms. S2V2 plus T2V2, you would add your real numbers times V2. So again, think of it as adding like terms. Closed under scalar multiplication, pick any real number, and then that arbitrary vector U. When you multiply C times U, C gets distributed, and you can multiply those constants together, and those are the weights of your vector. There is a theorem in 4.1 if you're following along in your textbook. The span of however many vectors are in your problem is called the subspace spanned or generated by those vectors. So if you have a set of vectors, the span of all those vectors is called the subspace spanned or generated by those vectors. Let H be the set of all vectors of the form A minus 3B, B minus A and B, where A and B are real numbers. Show that H is a subspace of R4, so that's why the vector has 4 entries. In a previous example, we had H had 3 entries, S, T, and 0, so that was R3. Okay, so what I'm going to do is I'm going to take this description and write H as a matrix using those 4 terms in order. If you separate them by A, the a terms, you have a coefficient of 1, -1, 1, and 0. There's no a here. So a times this vector. And then you sort the b's out. -3, +1, 0, there's no b, and 1. So it'd be b times this vector. The span of h, the span of these two vectors, no matter what weight or direction, h will be the span of those two vectors. And therefore h is a subspace of R4. These are R4 type vectors, 4 entries. For what values of h will y be in the subspace of R3 spanned by vectors 1, 2, and 3? Well, so vector 1, 2, and 3, if we can figure out what they span, then we'll check the value of y where that's possible. All right, so what I'm going to do is I'm going to take these 3 vectors given, respectively put them in columns 1, 2, and 3, and then vector y, I'm going to put it in the 4th column, and row reduce this augmented matrix. What you'll find is it reduces to, we got a little hitch here. Remember, we can't have a pivot in that last position and it be consistent. So if you have a row of zeros, then that entire row needs to be 0. H minus 5. If that's equal to 0, then what does h have to be? H has to be 5. So that is only consistent for h equals 5. And that would be the answer to that problem.